Alright, welcome everybody to Chapter 18 of Chemical Structure and Reactivity. I'm your host Palladium, and of course, here's a new update. I added two lecture assistants, Larry and Saya, to this lecture series, and they're going to be helping me with making notes on LaTeX, helping me with slideshow creation, and overall just making this lecture creation process a lot much smoother, so that you guys won't have to deal with delays, and I can get my lectures out there faster. And of course, here is the shoutout list both on YouTube and Discord. If you'd like to be added to it, by all means ask me. I'd be happy to add you to this growing list right here. So let's get straight into this, shall we? So what exactly will we be talking about in chapter 18? CSR has 21 or some chapters, and we're like almost at the end here. And so what exactly will we be talking? Well, in these later chapters, we're gonna get into a lot more math-heavy concepts. So while I'll still be going with a more conceptual route here, you will see that you'll have LaTeX node provided to help you with some of the mathematical equations. And of course, when you think of math in chemistry, it's hard not to think of quantum mechanics. And so this chapter will talk about quantum mechanics and also how that can relate to more spectroscopy. Back in chapter 13, I talked a little bit about spectroscopy and the different forms of it, such as IR, NMR, and also spectrometry with mass spectrometry. So to start, we'll first get started with some mathematical notes and concepts, and then dive straight into what quantum mechanics really is and how we can use that for spectroscopy. So here's a brief introduction of what we're doing. So if you guys watched my past lectures, you know that chapter 2 was my lecture on electrons. And the thing about electrons is that they are a fundamental particle of quantum mechanics and pretty much the base of almost everything in chemistry. And in that chapter, we pretty much introduced quantum mechanics and how that's different from classical mechanics. So, for example, hold up. Yeah. So, for example, in chapter 2, we talked about how quantum mechanics has discretized energy levels, while classical mechanics does not. It has continuous energy levels. And so when we talked about how electrons fit into these various energy levels and how these levels determine like if a photon is absorbed or not, we talked about electrons existing in wave functions. And what wave functions are essentially, instead of treating the electron as some sort of particle in a definite place, like think of a ball that you throw up, you precisely know its position. It's more of a fuzzy cloud, and that wave function is used to describe the probability of where that electron exists. So if you're in a region of high probability, will there be a high chance that you'll find the electron there? Yeah. But if you're in a region of low probability, then no. And so how we yield these probabilities is through the calculation of these wave functions. And by calculating the probability density by squaring the wave function, we obtain the probability density, which tells us in a tiny volume in 3D space, how likely are we to find some electron? Now, in this book, we're using only real valued wave functions. And when I say real valued, I mean functions that only take in real inputs and output real outputs, no imaginary components. But in fields such as, in later theory, if you dive into a book such as Landau or any advanced pieces of literature, you will find complex and imaginary numbers being used a lot of the time, especially for describing wave functions. And so for anybody who wants to get into quantum, one important thing to know is that to find the probability density for a complex wave function, you multiply it by its complex conjugate. Anyways, here's, in addition, one fundamental concept I suggest you guys keep in your head throughout this chapter. So when we talk about molecules, we previously talked about how electrons can have quantized energy levels, but so can molecules. And these energy levels exist in three forms. Translational motion, which is motion that occurs simply by moving a molecule around. Rotational motion, where we pretty much spin the molecule around. And vibrational motion, where the bonds themselves stretch and repel and overall vibrate. Now, while all of this motion stuff sounds cool, we first have to talk about, well, the base postulates of what we're looking into. So the entire framework of quantum mechanics are based on these first two wave functions, which is that if you have any quantum mechanical system, as long as you have the exact wave function, not approximate, exact wave function, you can derive any property of it that you want. And so you can calculate energy, positions of the particles, all of that just from the wave functions. And to obtain these properties, we use operators, which are mathematical objects that act on the wave function to yield these properties. Let's get a bit closer when we're talking about these operator things, though. So if we look directly at mathematics, the definition of an operator is simply something in mathematics that acts on some function to create a new function. Take, for example, if you remember back in Calculus 1, you covered differentiation with respect to a single variable, such as d over dx. Well, if we differentiate a function with respect to x, we can put that into an operator. And this operator, we can slap that onto any function that has only one input and one output and yield a new function. That's the entire point of differentiation. You differentiate some sort of function with respect to a variable to get a new function that describes the instantaneous rate of change at each unique input. Now, how exactly are we going to use operators in quantum mechanics? Well, in quantum mechanics, each quantity that we observe can be represented with an operator. And what I mean by this is that these operators act on the wave function to yield these quantities or properties of the quantum mechanical system. And a few examples include position and the Hamiltonian. Now, if you apply the position operator onto the wave function, you're going to get the positions of the particles in that system. But if we talk about the Hamiltonian, that's defined as the sum of both kinetic and potential energy in the system. And so if you can slap that onto the wave function, you get the total energy of the system. Now, here's an interesting thing when we consider operators on different functions. If we have an operator that acts on a function, a new function is generated, obviously. But there's one particular scenario where an operator is applied onto a function. And when it is applied onto that function, we yield that function times some scalar value. Scalar is just a unitless number. And this exact equation, a hat phi equals lambda phi, sums up pretty much what we're trying to solve in quantum mechanics. where if we apply this operator onto the function phi, we're going to obtain, I think it's phi. If we apply that to the function phi, we're going to get an associated eigenvalue. And these specific functions, where if you apply an operator onto them and they remain unchanged, these specific functions are known as eigenfunctions. And these are functions that simply remain unchanged and are just multiplied by a constant when an operator acts on it. One good example of this that you can take from calculus is any function of the form e to the power of a times x. A is just some number. X is, of course, our input. When we use the differentiation with respect to x operator on it, as per the chain rule, we get an associated eigenvalue of a. Therefore, making this function an eigenfunction when we consider differentiation with respect to x as an operator. Now, here's another postulate about quantum mechanics. Whenever we make a measurement of the value of some sort of observable, like we take the Hamiltonian operator and slap that onto the wave function, then the results will always yield one of the eigenvalues of the operator. Now, it's no specific eigenvalue, it's just a eigenvalue. And one example that we can use is if we have a molecule and we measure its energy, say for example we use the Hamiltonian operator, if we measure that energy, then the result will be some sort of eigenvalue that represents the overall energy of that system. Now, that's enough talking about operators. What about the functions that we apply those operators onto? Well, these functions are known as wave functions, and we look at them through something known as the Born interpretation. And what the Born interpretation is that the probability of finding a particle in some tiny value, dV, if you remember from your calculus class, d in calculus just means a tiny bit. So if we find the probability of finding a particle in some tiny value is going to be the wave function times its complex conjugate. And that's going to be for complex valued wave functions. Of course, we're dealing with real valued wave functions in this book, so we just square the wave function. Now, another property of wave functions is if we take the integral over all space of the square of the wave function, then that entire integral has to be equal to 1. And you can think of it as this, right? Say, for example, you're watching the Knicks versus Spurs. I know that I watched it, everybody in my town watched it. Really fun NBA final series. And say, for example, a basketball player on the Knicks is making a shot. There's the sum of all probabilities of where a shot will go, whether a shot is going to be a 3-pointer, whether it's going to be a 2-pointer, whether it's going to completely miss the net. All of those probabilities summed up is always going to be equal to 100%, which we just represent as 1 in this scenario. And that's one of the fundamental properties of any probability distribution, that its total area will always be equal to 1. And therefore, we need to normalize the wave function so that its total area is only equal to 1. Alright, so that's enough about the starting points of quantum mechanics. I will let y'all post any questions that you have in Lectureland. I'd be happy to answer them. And we're going to do this for about 2 minutes. Keep going with the lecture. So let's get into the more fun, I'd say the more advanced stuff in quantum mechanics right now. So when we talk about quantum mechanics, we have to solve for the wave functions in a few particular scenarios. And this first scenario is often known as the particle in a box. And here's how the scenario goes. Imagine that, wait, not a particle in a box, but we're building up to it. So let's first consider a particle that moves in just one dimension. And we have a potential that we constantly apply to that particle. As you can see, our Hamiltonian operator, we can write that in explicit terms. And to find the necessary eigenfunctions and eigenvalues of this operator, well, we need to solve the eigenvalue equation, which is the Schrödinger equation, actually. And when we're going to be solving for this, there are going to be two cases. So remember what I said about the Hamiltonian operator. It's simply an operator that represents the sum of both kinetic and potential energy. And so we're going to get one case where our logic's perfectly going to be fine. And in that case, the potential is going to be less than the total energy. I mean, yeah, the potential always has to be less than or equal to the total energy. You can't exceed it. But in quantum mechanics, there's a second case where all your intuition gets thrown out the window. And that's when the potential is actually more than the total energy, which doesn't make any sense in classical mechanics. I mean, if you have the total energy, unless the kinetic energy is negative, which it shouldn't be, then the potential energy should never be greater than the total energy. But quantum mechanics is completely fine with this. And we can see it in these two cases. So for this eigenfunction problem, let's look at the first case, where the total energy is greater than the potential, which is just normal. Well, we can actually come up with a wave function of the form of combinations of trigonometric functions. And so you can see we have cosine functions, we have sine functions, and overall, we're doing pretty good. We have this pretty simple wave function that fits the eigenvalue problem and actually satisfies this problem too. But for the non-classical case, where the potential is more than the total energy, we have to use a different wave function form. And so instead of using a combination of sine and cosine, we have to use an exponential function. exp, if you don't know, that's just e raised to the power of whatever's in that parentheses. And the reason why we choose this form as the wave function is because the second derivative of this wave function is the exponential times some sort of constant as per the chain rule. And so this definitely fits the eigenvalue problem. Now, I want you to take a closer look at this function. If you see that particular term, k prime, we can derive the value of k prime and express it in terms of mass, potential, total energy. I mean, overall, we can actually obtain k prime and pretty much put that into the wave function form. Now, thankfully, when we use wave functions of this form, k prime is the square root of a positive number, meaning that we don't get any imaginary business over here. And as the potential becomes larger, k prime also becomes larger. And as you can see in the wave function, k prime times x, that's a negative term, signifying exponential decay. And as k prime grows more positive, exponential decay will happen much more quickly. And going back to the classical versus non-classical case, you can see the differences in how these wave functions look visually. As you can see, the classical case is simply a sinusoidal function, pretty neat stuff. It's periodic, nothing wrong with it. But for non-classical, we simply just get exponential decay. Now, on one random day, what if I just wanted to force this particle into a restricted region? It's not going to move freely on the x-axis or on the number line. No, it's actually going to stay in a sort of box where it's going to be restricted to just the boundaries. And I'll define this box with the length L. But how exactly am I supposed to prevent this particle from escaping the box? Well, one easy way to do it is to have the potential inside the box on that number line be 0. However, outside of that box, that potential is going to be infinite, meaning that it's not going to be able to escape theoretically. And because the potential is 0 within the box, we can simplify the Schrödinger equation and solve for both the energy and k, which will be used for eigenfunction solutions. Now, here's an important thing to know. When we talk about wave functions, and especially for a particle in the box, what we want to do is we want to restrict that wave function so that only non-zero values are in the box region. And what we have to do is we have to make the wave function 0 beyond the points of the boundaries. And we must do it in such a way that the wave function must not suddenly jump from one value to another. It must reach that value in a smooth fashion. So to avoid this jump, we have to impose two specific boundary conditions. The first boundary condition states that if we evaluate the wave function at x equals 0, that's going to be 0. And if we evaluate it at x equals L, that's also going to be 0. And by doing this, we're going to be preventing the wave function from actually having a non-zero value beyond the boundaries of the box. And we can consider the classical case where we use sinusoidal wave functions. We can use the classical case and test out these boundary conditions to find desired values for our constants. So let's first talk about this first boundary condition, that if you evaluate this wave function at x equals 0, we're going to get an output of 0. And if we evaluate that, we're going to get the wave function of this form. As you can see, the term including a cosine kx, that immediately gets turned to 0. And therefore, we have to say that a must be 0. However, if we evaluate the function at x equals L, we find out that b has to be 0. But obviously, multiplying anything by 0 makes it 0. So our wave function should be psi x equals 0, right? Well, there's an issue with that. And the issue with that is when we define a wave function, we define it as the area under that wave function, the integral of that wave function over all space. It has to be equal to 1. And we're going out here saying that that wave function has to be 0 everywhere because of the boundary conditions. But if it's 0 everywhere, then the integral is going to be 0. And as you know, 0 is not 1. So what are we doing here, and how can we fix this problem? Well, what we can do is we can first rearrange to find k. And by rearranging for k and substituting it back into our wave function, we actually yield a wave function that, one, both satisfies the boundary conditions, and two, is an actual wave function. And as you can see, here are some visualizations for the particle in the box wave functions. We have both negative and positive regions, and in addition, we have nodes, where the wave function evaluates to 0. But regardless, as you can see, the boundary conditions are satisfied, and the integral should make it so that it's a valid wave function. Now, if we square these wave functions, well, squaring anything makes it positive, or any real number. Squaring any real number makes it positive. And since we're dealing with real valued wave functions, our probability densities are going to be all positive, and the nodes are actually going to be retained. And you can see it for these different energy levels. N equals 4, for example, has 3 nodes. Nodes are simply regions where the function evaluates to 0, which don't include the boundary conditions, by the way. So we have 3 nodes in probability density for n equals 4. And as you can see, for n equals 4, we also have 3 nodes. Pretty amazing stuff. And by integrating the wave function over the length of the box, we find out that simply because the total integral must be equal to 1, we can calculate the value of b based on the length of the box. Now, on a side note about wave functions, when we're talking about the integrals of wave functions, imagine that I have 2 wave functions, wave function A and wave function B. If I take the product of that and take the integral of that product over all of space, it accidentally said over all time, but all space. If we take the integral of that product and that integral is going to be equal to 0, then those wave functions are orthogonal to each other. All right. Now, here's one interesting thing that I found while I was studying this chapter. And remember when we were discussing about energy levels and the different wave functions and probability densities that were associated with these energy levels? Well, that principal quantum number, n, it was always an integer above 0. It was never exactly 0. And why is that? Can't we just have a quantum mechanical particle be still? Unfortunately, while that is possible in the classical mechanics world, at least, that's impossible in the quantum mechanics world. And that's because whenever we measure a quantum mechanical particle, we're always going to get some sort of uncertainty, whether it's in its position or in its momentum. And therefore, hard baked into the universe, like this is a feature of the universe, not a bug kind of thing. Hard baked into the universe is uncertainty that we can't even measure these particles to full precision and accuracy. And therefore, because of this, even if these particles, like quote unquote, stop moving, they actually never stop moving. And movement means energy, so there will always be some energy. And this is precisely known as 0-point energy. Now, after those quick notes, here's something I want to tell you guys. When I talked about the particle in a box scenario and the wave functions, the reason why we picked that 1D scenario is because derivation was simple. It was simple for us to look at the boundary conditions of those wave functions And it's simple for us to just look at 1D space. But for other particles in 2D or even 3D space, derivation gets a bit more difficult. And you can see it right here. We have a particle confined to a 2D plane, and instead of having one quantum number, we have two different quantum numbers that dictate the nodes in these wave functions. Now, one interesting thing that arises when we look at the wave functions for 2D is that there are wave functions that have the same energies but are different. Take, for example, the wave function with nx equals 2 and ny equals 1, and the wave function with nx equals 1 and ny equals 2. Calculating the total energy, calculating the orbital energies, they're equal, but as you can see, they're completely different. So that means that we get degenerate wave functions. All right, and here is the second scenario. So before I continue with the harmonic oscillator, see what the time is, 6:44 New York time. Or it's 6:45 New York time. All right, I will give you guys 2 minutes to get some questions ready and just ask them in Lectureland if you have any. So going on for the harmonic oscillator, in addition to solving the Schrodinger equation for a particle in the box, we have to solve it for pretty much a mass on a spring. And if you guys know IR spectroscopy from, I'd say, chapter 13, then, well, you know that pretty much so much of vibrational motion, you can just summarize that with the harmonic oscillator. And so for a simple harmonic oscillator, we can yield a Hamiltonian that we can write out in explicit terms. But let's get into the actual science behind a harmonic oscillator. Not the equations, just the science. And here's how exactly it works. Imagine that you have some sort of mass on a spring, and you stretch out the spring a little bit. In an ideal system where friction doesn't exist, what's going to happen is once we release that spring, a restoring force is going to come into play. And that restoring force is going to try to get that mass, which has been displaced by us, it's going to try getting that mass back to the original equilibrium position. And the restoring force is calculated as the negative of K. K is known as the spring constant. The restoring force is calculated as the negative of the spring constant times our displacement. And if we want to calculate the amount of potential energy in said spring, what we can use is we can define some calculus here and use separation of variables to find out that the elastic potential energy is equal to 1/2 times K times the displacement squared. And this will especially be useful for spectroscopy. And the reason is bonds are not static. They're not anything like bones where they exist in rigid structures. No, bonds stretch out. And what I'm saying is through Coulomb repulsion, attraction, these bonds vibrate and move back and forth, just like a harmonic oscillator. And when we're looking at the frequency of an oscillation for a mass on spring, we could define the frequency as the square root of the spring constant divided by the mass. And therefore, by plugging in an equation for the displacement over time, we can get a function for the potential over time. Not potential as a function of displacement, potential as a function of time. And solving for the Schrodinger equation for simple 1D mass-on spring, we can find out that we have different eigenvalues. And these eigenvalues are quantized and follow a certain formula. And this formula is dependent on something known as the vibrational quantum number, which instead of being the principal quantum number, solely dictates vibrational motion. Now, the classical case of a harmonic oscillator was cool, but what if we talk about quantum mechanics? Well, let's get into the quantum case, where let's first consider a normal harmonic oscillator. If we extend that spring by a certain displacement, we can trust in the laws of physics, unless somebody applies some external force, that mass will never reach a displacement that's greater than the displacement that we've done. And therefore, we ensure that the potential is always going to be less than the total energy. But if we go further than that, then the potential energy is more than the total energy. And in classical mechanics, this absolutely wouldn't pass. But in quantum mechanics, we're completely fine with this. And in this case, the non-classical case, the wave function simply decays faster instead of everything breaking down, similar to the wave functions for a particle in the box. And in addition, we can see the associated wave functions for the different eigenvalues for a harmonic oscillator. So we talked about energy levels, eigenvalues, all that. But how does that connect to spectroscopy? Well, in past chapters, we talked about how photons are emitted and absorbed when a molecule moves up and down in energy levels, whether it's translational, whether it's vibrational, whether it's rotational, doesn't matter. All, all that we need to know is that photons are emitted and absorbed, pretty much. And this is especially useful for IR spectroscopy. If you remember chapter 13, I talked about how certain photons in the infrared range can get absorbed by molecules to move up in the energy levels, in precisely their vibrational energy levels. And by absorbing a photon, a molecule can go from an initial ground state to an excited state. Now, there have to be certain rules for these transitions. I mean, molecules can go willy-nilly all over the place and transition wherever they want. No, they have to transition to proper energy levels based on where they are now. And there are two specific types of transitions: allowed and forbidden transitions. And selection rules tell us, hey, is this transition allowed or forbidden? And one such selection rule is known as a growth selection rule, which refers to an overall property of a molecule, and often states that if we have two values, that the difference in those two values has to be some constant value. Now, there are photons that can allow for allowed transitions, but without any molecules in that energy level, no transitions happen in real life. It's kind of like preaching a message to a crowd, but nobody pulls up. It's like doing a concert, but nobody even books tickets to your concert, pretty much. And if we have molecules, not only can we have them absorb photons, we can have them emit photons. whether it's spontaneously with them going down energy levels, but also through stimulated emission, where we send out a photon to make these molecules go down in energy levels artificially. All right. And for IR spectra, these are heavily correlated to vibrational energy levels. As you can see, there is a comparison on your right for vibrational energy levels of carbon monoxide and iodine, I think monobromide. I forgot my nomenclature. But we can model this problem with the bonds vibrating with a harmonic oscillator. But here's the issue. Instead of having one mass on a spring, we pretty much have two masses, which are the atoms. We have two masses on a bond, and we essentially have two masses on a spring instead of one. So it would be really, really cool if we can treat it just like a one mass problem. And that's where the reduced mass comes in. And by using the reduced mass, we can calculate the frequency of oscillation and the quantized energy levels. Now, when we're talking about the physical phenomenon of these bonds stretching and vibrating, a harmonic oscillator is simple, right? It seems befitting. Bonds go from long distances to short distances. They're pretty much like springs themselves. But the issue with using a harmonic oscillator, although it seems simple and elegant, is that its vibration, like you can't model it realistically with the harmonic oscillator. And so therefore, we can use potentials such as the Morse potential. I've given you the explicit um, form of the Morse potential, but you can see on the left and right, we do get descriptions of what the Morse potential does to both energy levels and how it describes energies between two different atoms based on separation. And in fact, you can see a set of wave functions from the Morse potential contrasted to the harmonic oscillator wave functions. The Morse wave functions are on your left, and the harmonic oscillator ones are on the right. Now, I talked about diatomic molecules enough already, right? It's a simple two mass on a spring problem, and it's pretty simple. You can model it with Morse potential or harmonic oscillator. Pick me, choose me. But when we move beyond diatomic molecules, we have to account for different stretches in different normal modes, such as symmetric or antisymmetric stretches, or different sorts of bends. And so that's where IR spectroscopy and modeling the potential between two different atoms can get a whole lot more complicated. But that's enough about IR spectroscopy for now. Let's get into another form of spectroscopy that relies on vibrational energy levels, known as Raman spectroscopy. I like to pronounce it Raman, but honestly, it's your pronunciation in the end. So, this is another form of spectroscopy that looks at the vibrational energy levels of a molecule. But I want to take you back to what IR spectroscopy does. It simply measures the absorption of IR photons at a specific wave number or frequency. However, what Raman does is it measures the scattering of photons instead of absorption of photons. And how exactly this works is when we have a photon that interacts with a molecule, we often get elastic scattering, where the energy of that photon is going to come out the same as when it came in. However, there does occur inelastic scattering, where the energy of the photon is different in some way. And by using highly precise tools, we can measure the inelastic scattering of photons. And that thus yields us Raman spectroscopy. And in addition, here's a fun fact. C.V. Raman, the guy who worked on this, actually won the Nobel Prize. He was the only Indian to ever win the Nobel Prize and do his work in mainland, dare I say, also colonial India. All right, but going on, that's enough about the harmonic oscillator, Morse, Morse potentials, solving for the Schrodinger equation for all that. Let's talk about another case. And in this case, we're going to be discussing rotational motion, where those molecules rotate in space. And we can use rotational dynamics here to define an object known as the rigid rotor. And the rigid rotor is an object that pretty much spins around. That's it. And we can define this rotor with the moment of inertia based on the mass and its radius. And for those who don't know rotational dynamics, the moment of inertia is simply an equivalent to mass that pretty much changes depending on what axis you're on. So take, for example, you have a pencil, right? If I'm holding that in its center, I can spin it around on different axes. And based on these different axes, no matter if I apply the same force to it, what's going to happen is we're going to get different angular velocities, and these revolutions happen at different rates. And by looking at the moment of inertia, we can define the energy levels for rotational motion based on the moment of inertia and the reduced Planck constant. And as you can see in this equation right here, J is known as the rotational quantum number, and B is known as the rotational constant. And we can adapt this idea of a rigid rotor to a diatomic. And the only thing we have to change here to solve for the energy levels is simply replace that m term in the moment of inertia. We simply have to replace that with the reduced mass. That's all we have to do since we're treating this like one body problem. And you can see we get different energy levels with larger and larger gaps based on the rotational quantum number, J. Now, here's enough about talking about rotation and vibration as separate things. Molecules do both. Molecules do all three, matter of fact. They rotate in space, their bonds vibrate, and they move physically. They do all of that. If we consider rotation and vibrational motion, we can separate these different types of motion onto different time scales. And if we consider both of them, what we can do is we can combine the energy levels of both the rotational and vibrational energy levels. We can combine those energy levels to create a sort of total energy level that sums both rotational and vibrational motion. And as you can see, it can get pretty complex when we're considering both. When we look at something like rotational motion, instead of using IR photons, we often use microwave photons. But you can see we can get a whole load of different transitions here for both rotational and vibrational levels. And in fact, we can use this to both simulate and actually base our IR spectrums off of that. So, for example, with carbon monoxide, we get both different rotational and vibrational energy levels that correspond to these different peaks. And that central line in the middle, that's going to be the angular velocity. And so, to wrap this all up, here are 4 key points that you need to know if you're going to be reviewing this for an exam. The first point is that operators are using quantum mechanics and act on functions, meaning that if we have an operator and we apply that to a function, we get some eigenvalue problems, given that, well, the function is an eigenfunction. And using these eigenvalue problems, we can use them for different cases where we'll need to solve for the Schrödinger equation, such as the rigid rotor and the harmonic oscillator. And when we're solving these equations, I want you to let go of all of the logic you had back when you did classical mechanics. As you can see, we've had cases where the potential can be more than the total energy. And as for the final point, based on these quantized energy levels, both rotational, vibrational, we can get different forms of spectroscopy and we can calculate spectra and match them up to experimental spectra. And as for a sneak peek in the next chapter, I know I love giving you all sneak peeks. So the next chapter will talk about chemical thermodynamics. And I'm not going to talk about chemical thermodynamics in the sense that a lot of these Olympiad textbooks do, where they give you Gibbs free energy, they give you these definitions, but you don't get any proper understanding of thermodynamics. No, we're going to get straight into state function, equilibrium, gases, statistical mechanics, and a whole bunch of calculus, meaning that you will be provided with more math notes for chapter 19. And as for when that lecture will happen, remember my lectures always happen weekly. They happen on a Sunday, Sunday, 6 p.m. New York time on the CODS Discord server in the lecture hall channel. And so for anybody watching on YouTube or anybody watching it on Discord right now, I suggest you go and attend the next lecture. We would be real happy to have y'all here and have these lectures grow into something that the Olympiad community can actually use for understanding. And I'm your host, Palladium. This is going to be the end of chapter 18. See y'all and take care.